Alright, so for section 11.3, we are going to look at representations of functions as power series and Taylor series. Well, so in this section, we are going to obtain representations of functions using geometric series. This is an alternative to what we did in the first section using Taylor and Maclaurin series, which actually will go back to them. But in the meantime, we're going to look at a new way to obtain series. Of course, these series, since they represent functions and, well, of course, they give rise to polynomials, we can do calculus with them, those such as differentiate and integrate them. And we're going to take advantage of those two operations in order to obtain other power series for other functions. All right, so let's see. Well, in the end, we're going to evaluate integrals, and we're going to obtain Taylor and Maclaurin series for elementary functions. All right, so representations of functions using geometric series. So one thing that you might want to recall is the form for the geometric series. Well, here it's given in terms of x, but initially in chapter 10 we did the following. We got sigma a r to the n, and starting at 0 to infinity, all right, where a is a multiple, it's a number that multiplies, that's a sub 1, and r is the common ratio and n is the power. So notice the similarity here. In this case, we have that series. Well, let me write it down over here. That sigma a r to the n, and starts at 0 and goes all the way to infinity. And we found out that whenever the geometric series converges, that is when that value of r, which by the way, let me highlight it, this value of r in this case will be represented by x. So the geometric series converged whenever that r is less than 1. The absolute value of r is less than 1. And if you in that case, we were able to find the infinite sum given by a over 1 minus r. All right, which in this case, this one right here resembles that quantity there. That is that we're going to use this geometric series to obtain power series for rational functions. So in section 11.1, we obtain a power series for the sine function, for the cosine function, and now we're going to obtain we also did for exponential function, but we didn't get it in sigma notation. We're going to do it here, and we are going to look at new techniques to obtain those power series. All right, so if we consider this f of x equals 1 over 1 minus x, well, think of this as being an a equals to 1 for the sake of simplicity. All right, of course, what if I wanted to obtain a power series for I don't know, maybe 1 over 1 minus x cubed? Well, in this case, we need to generalize this x instead to be a u, because in this case we will find power series for more composite functions. And well, I think the best way here is to have a look at one example, and I'm going to leave this visible so you can refer to the formula that we're using, the form that we're using rather. So express f of x equals 1 over 1 plus x squared as the sum of a power series and find the interval of convergence. All right, well, so in this case, so we want to rewrite this function in a way that it looks like 1 over 1 minus u, and sort of is, because well, we already have the 1 and the 1. However, here we have a plus, but we need to make this look like a minus. So let me rewrite the function then in the following way. So that means we can write that a minus, provided we write a minus x squared inside of the parentheses here. All right, and well, if you think of the following, so now it looks like 1 over 1 minus some u, where in this case the u equals negative x squared. So what I'm going to do here is I'm going to rewrite this function in terms of u. That is 1 over 1 minus u squared, which is what we wanted, and then just use the power series for the geometric series. Alright, and now that we are done writing the sigma series in geometric form, we may go back, substitute for u in this case, which in this, well, for u, which in this case is negative x squared to the n. But of course, in this case, whenever you obtain a power series like this, it's important to simplify this. Notice we have a negative 1 multiplying the x squared. This is the same as saying negative 1 times x squared to the n, so the n will affect both the negative 1 and the x squared, leaving us with sigma n equals 0 to infinity of negative 1 to the n power, and n power n to times 2 in this case, because power of another power will multiply the exponents. That's x to the 2n. Alright, so we reach our first part of the goal, which is obtaining the power series in sigma notation. But they're also asking us to find the interval of convergence, and well, for the interval of convergence, we need to do the following. So for interval of convergence is that is going to be, well, keep this in mind, whatever absolute value of u has to be less than 1. Alright, that means in this case, well, negative x squared less than 1. Alright, and in this case, well, the absolute value of a negative quantity is positive x squared less than 1. But in this case, recall that whenever we take the square root, because x can be anything, we need to have this as absolute value of x less than 1, and then from here it follows that x less than 1 but greater than or equal to negative 1. Alright, and that's the interval of convergence. It goes from negative 1 to 1. So this is in inequality version, but of course you can write this in interval notation, which might be more convenient. Alright, so that's one example of how we obtain the power series of this rational function, taking advantage of the geometric series. Alright, the geometric series form. So now let's look at another example. Well, for example number 2, find the power series representation of f of x equals 1 over x plus 2. Number 1, I would like to rewrite this in a different order. This is equal to 1 over 2 plus x. Alright, so number 1, there is a little issue right here. In order for us to be able to use the geometric series form, it needs to look the following way. Sigma n equals 0 to infinity, that's an x to the n or u to the n. That has to be 1 over 1 minus u. But in this case, well, we have a plus, but on top of that we have these 2. So we need to get rid of that too. Alright, so well, there's a couple of ways to get rid of the 2. I guess the easiest one is to factor out the 2 from the denominator in this way. 1 over 2 times 1 plus, well, what quantity would give us back the x? Well, in this case, x over 2. Alright, and I know this one is going to take a few more steps than usual, but well, you'll see. So this will be equals to, so I'm going to factor, so this 2 in the denominator is a 1/2 outside, and this is 1 over 1, and I'm going to turn this plus into minus negative x over 2. Okay, from here we are going to obtain the following. Well, that's a 1/2 1 over 1 minus u, where in this case, let's indicate that u equals to negative x over 2. So now that we have this 1 over 1 minus u, we may use the geometric series. Don't forget the 1/2. Sigma equals 0 to infinity, and that's u to the n, where in this case, that u is negative x over 2 to the n power. And well, the rest of the problem would be to expand again the negative. Do recall that we have a negative. This will be, okay, let me keep writing this 1/2 right here outside of the sigma. I'll put it inside in a second. Sigma n equals 0 to infinity, and that's going to be negative 1 to the n, x to the n, 2 to the n. Now check this out. So in this case, notice we can further simplify this, combining this 2 to the n with the 2 outside. This 2 outside is a 2 to the first power. 2 to the first times 2 to the n. Recall that in this case, we add the exponents when we have the same base. So n equals 0 to infinity. All right. And in this case, so that's a negative 1 to the n, x to the n over 2 to the n plus 1. And that's the power series for this rational function. And well, they didn't ask us to do it, but of course I'm going to do. I'm going to find the interval of convergence. So the interval of convergence so in this case, that's the absolute value of u less than 1, and in this case the u, recall that u is negative x over 2. And I'm gonna go back to the same color just so you can relate. That less than 1, and well, absolute value of x over 2, well, that's going to be, let me just take out the negative, and I'm going to keep the absolute value bars on both sides, on the left hand side. Why do I do that? Because, well, technically when I have absolute value of negative x over 2, that's the same as saying absolute value of negative 1 times absolute value of x over 2. And I'm going to keep these absolute values for x over 2 and just simplify the absolute value of negative 1. So that's an x over 2 less than 1. And from here it follows that x over 2 less than 1 and greater than negative 1. And solving the inequality for x in the middle, multiply the three sides of the inequality by 2. That's going to give us negative 2, negative 2 and less than x less than 2, or from negative 2 to 2 in using interval notation. So that's inequality notation and interval notation. For example number 3, let's find the power series representation for f of x equals x cubed over x plus 2. And well, in this case, I'm not going to go through the entire process again, because if you can think of the following, right here. So f of x equals x cubed over x plus 2. Well, we already have a series for 1 over x plus 2. All right, so we can multiply the x cubed outside. All right, and instead of going through the entire process, because we can just use our result from the previous part. So we already got a series for 1 over x plus 2, which is this series right here. So what I can do is x cubed times the sigma series, the series from before, and well, in this case what we can do is introduce this x cubed over here. But what are we going to have? So in this case, technically this is an x cubed over 1, all right? and I'm going to multiply x cubed times x to the n. When we have the same base, what we do is add the exponents. That is sigma n equals 0 to infinity of -1 to the n x to the n plus 3 over 2 to the n plus 1. Final answer. All right. Well, let's do some calculus of series. Well, so we already did a little bit of the derivatives to obtain certain number of terms of a series using the Taylor or Maclaurin series, But in this case, well, this power series, well, in this case, what we have here is the generic form, which can be centered at any value of a, and or can be centered at the origin. All right. So, well, just expanding the series a little bit, a few terms. Well, for n equals 0, we have c sub 0, which is this one, x minus a to the 0. Well, that's just 1. And then for n equals 1, c sub 1, x minus a to the first power, which is this invisible one right here. For n equals to 2, c sub 2, which is the c sub 2 here, x minus a to the second power, and so on and so forth. All right, now if we observe this series, this infinite series, it's a polynomial, and polynomials are differentiable everywhere and integrable everywhere as well. So for this reason, we can take the derivative of this polynomial, and we can also integrate this polynomial with a little difference. Be careful here, be very, very careful. So the original function f of x, which is this series right here, I would like you to observe, or rather focus on the starting index here. And what's going to happen here? What happens when you take the derivative of this? Take the derivative of c sub 0, which is just a number. The derivative of a number is 0. And now our first term is c sub 1. For this reason, see how the starting index on the derivative now starts at 1. That's something you want to be careful of, all right? However, that's not the case of the integral. In fact, that c0 remains, but all we add is a constant of integration. All right, so here is the thing. When it comes to finding the radius of convergence, or you might recall that we did the ratio test or the root test, whatever test was better or easier, and then we needed to test both endpoints to determine whether the series converges or diverges at the endpoint and find a more clear, or a more accurate interval of convergence. It could be exclusive on the endpoints, inclusive on both endpoints, or exclusive inclusive or inclusive exclusive. Now, when it comes to taking the derivative of a series, the radius remains the same. All right. So let's see. Let me highlight that with a different color. So here, that's what this sentence is telling us, that the radius remains the same. However, the interval may not be the same. In fact, it is possible that the interval of convergence may be the same as the original function. It might go from both exclusive to maybe both inclusive, or maybe from both exclusive to one inclusive, one exclusive. All right. So that's so it's important to check for the interval of convergence, or rather at the endpoints. And we're going to take advantage of these properties of differentiation and integration to obtain power series for new series. All right. So, for example, find a power series representation for f of x equals 1 over 1 minus x quantity squared. All right. Well, the most natural thing to think about, just the same way we did before, is to relate this to 1 over 1 minus u. all right? Or, well, we use R or U, that's fine. However, now, okay, yes, we have a 1 minus U, if you will. However, this whole quantity is squared this time. Well, so how do we go about obtaining a power series using the using the geometric series? Well, so we need to think. So this is what we're going to do. We need to relate. We still need to relate this 1 over 1 minus x quantity squared relate to 1 over 1 minus x. And well, in this case, if it may not be that straightforward, but if we think of calculus of functions, we can think of the function whose derivative is this one. Well, and for example, let me rewrite it over here. So f of x equals 1 over 1 minus x, all right, which is 1 minus x to the negative 1. If we take the derivative f prime, that's going to be negative 1 times 1 minus x to the negative 2 times, by mini chain rule, the derivative of the inside, which is negative 1. Which in this case, well, it's going to be negative times a negative, that's a positive. And this negative 2 exponent can be rewritten as 1 minus x quantity squared, all right? So we're going to use this idea to obtain a power series. And let me rewrite the whole sentence, as in the previous page. So I'm going to start writing 1 over 1 minus x equals to 1. Okay, I'm going to leave some space, you'll see. 1 plus x squared plus x cubed dot 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 plus dot 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 goes on forever equals sigma n equals 0 to infinity of x to the n. So this is what we're going to do. We are going to differentiate the three sides of this definition. ddx, ddx, all right? So let's take the derivative of 1 over 1 minus x. Well, we already did, so that's the result that we want to obtain. That's 1 over 1 minus x quantity squared equals the derivative of 1, which is 0, the derivative of x, which is 1, the derivative of x squared, which is 2x, the derivative of x cubed, which is 3x squared, and then plus, if we had the x to the fourth term, that's 4x cubed plus dot dot dot. We don't need that many. And well, in this case, when we differentiate the series right here, all we have to differentiate is x to the n, which is what we did, differentiate x to the n terms. That is sigma n x to the n minus 1. But be careful here, because do you see what happened with the first term? The term corresponding to n equals to 0, that became 0, that canceled, and now the first legitimate term that starts the series at is when n equals to 1. So n equals to 1. And well, so let's see. Is there anything interesting that we can do about it? Well, so maybe rewrite the test in an easier way. So you might recall the shifting in the shifting index that we did before. So this is fine, this is a final answer. However, in this case, what I'm going to do is test the endpoints to find the interval of convergence. All right, so in this case, I would like to write this series in a more easy way. So I'm going to do this by shifting the indices. So I'm going to subtract 1 to start it at 0. When I subtract 1, I need to add 1 over here and add 1 over here, all right? So that's going to become sigma n equals 0 to infinity that's an n plus 1 x to the n, because n plus 1 minus 1 is just n. Alright, and I'm going to, well, we know from here, because this comes from the geometric series, technically the u that is used in here, so u is less than 1, where u in this case is x, less than 1, that means x less than 1, but also greater than or equal to negative 1. So in this case, because for derivatives, it is possible that that the interval of convergence changes from maybe exclusive to inclusive or something like that. So we need to test. Let me use a different color here to test x equals negative 1. So that's going to be sigma n equals 0 to infinity n plus 1. That's going to be a negative 1 to the n. Alright, and well, that's going to be exactly, that's actually, okay, n equals 0 to infinity, negative 1 to the n, n plus 1, and in this case, because we have that alternating factor, we can use the alternating series test. So using the alternating series test, we take the limit of the expression without the alternating factor. That's the first condition. And well, in this case, the limit better be 0, so we can do the second condition, which is the non-increasing. But in this case, well, the limit at infinity, that's infinity plus 1, that's still infinity, so diverges. So diverges at the lower endpoint. So that means this parenthesis right here for negative 1, it's still parenthesis, is exclusive. When we test the upper endpoint, test x equals to 1, so we get sigma n equals 0 to infinity n plus 1 times 1 to the n. But what's 1 to the n? That isn't that simply just 1? And that sigma n equals 0 to infinity n plus 1. And well, let's look at this series. It's very similar to the previous one. We can use the n-term test for divergence by taking the limit and approaches infinity, and if the limit is either d/e or infinity, d/e, or any number different than 0, which in this case is infinity, it's not equal to 0, then diverges. Recall that this test only tells us about divergence. Alright, diverges. Right, that's one more exercise, alright, and it's also exclusive on the upper endpoint. Alright, let's look at another example. So one example is to find the power series of f of x equals ln of 1 plus x. Alright, so now can you think of what can be done to obtain ln of 1 plus x? And you can think about the operation that we did in the previous example. Notice we took the derivative of that function to obtain the derivative of the function that relates the geometric series 1 over 1 minus x. So can you think of maybe another operation? So what operation gives us ln of 1 plus x? All right, so let's see, let me write it down. Over here. For example, if I think of a calculus operation that gives me ln of 1 over x, that's integrating 1 over 1 plus x with respect to x. That's going to give me ln of 1 plus x plus c. So that means that in a very similar way that we did it with with the series before, I'm going to do some operation here. However, it's important that you think of the form, because here we have a 1 over 1 plus x. and so we may need to rewrite this. Let's see. So number 1, that's 1 over 1 plus x, isn't it the same as 1 over 1 minus negative x, all right, which in sigma notation is the same, n equals 0 to infinity of negative x to the n. All right, so this is the same as saying u equals negative x, 1 over 1 minus u, and then here we have sigma n equals 0 to infinity of u to the n, where u is negative x. All right, so that means that if we expand this a few terms, 1 minus x plus x squared minus x cubed plus x to the 4th, etc. It's an alternating series, so minus dot 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 goes on forever. All right. So, okay, so in this case, we're going to do the integration operation to obtain a power series for ln of 1 plus x. Let's go ahead and do that. So I'm going to take this quantity right here, 1 over 1 plus x, and I'm going to take this quantity right here, which, by the way, let me rewrite this again in sigma notation. N equals 0 to infinity. This negative x to the n is the same as saying negative 1 to the n, x to the n. I'm going to write this one right here. Sigma n equals 0 to infinity, negative 1 to the n, x to the n. And well, in this case, we are going to integrate both sides of this definition. Integral with respect x, integral with respect x. And yes, this may look a little bit complicated, but think about this. All you're integrating is x to the n. So yes, what we got for the integral of 1 over 1 plus x, didn't we get the ln of 1 plus x as we desired before? And well, in this case, the integral of simply x to the n, so that simply will be, I'm going to leave a space here, you'll see why. Sigma n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. All right, and of course the space is for the plus c because of the constant of integration. All right, and this is the result that we wanted to obtain. That's how we obtain a power series representation for the logarithmic function. So just to summarize briefly, well, not yet. We can summarize this in the next, after the next example.